whenever you are having a Fourier series coefficient, I'm talking about the complex Fourier series coefficient, here represented as AK. Okay, generally we represent it as CK, but here it is given as AK, right? So whenever the signal x of t is real, then we found out the nature of AK to be even conjugate. To be even conjugate. So here if it is real plus even, here also we have seen real plus even. Here if it is real plus odd, here we have seen it to be imaginary plus odd. So these are some things that we have learned in the last class. Now let us look at the first option. Because in the question, it's given that x of t is having a complex Fourier series coefficient as AK. Because the formula is suggesting the same thing, that AK is the complex Fourier series coefficient. And the values of AK is mentioned in the question. The values of AK are mentioned as 2 minus j, 0.5 plus j, 0.2, 2j, 0.5 minus j, 0.2, and then you have 2 plus j, right? So it is also given that the values of AK is equal to 0 for the value of k, mod of k, which is greater than 2. So whenever you are increasing the value of k, whether it is positive side or in the negative side above 2, the value is going to be equal to that of 0. Then which of the following statements is true? Option A says that x of t has finite energy. X of t has finite energy because only finitely many coefficients are non-zero. Finitely many coefficients are non-zero. So x of t is a finite energy. Is it true that x of t is going to have a finite energy? Because when we talk about a Fourier series, we are talking about the power signals. We are talking about the periodic signals, which are power signals. So in the case of power signals, we very well know that the energy is always going to be infinity. So whenever we are talking about a power signal or a periodic signal, we will have the energy value to be equal to infinity, always. Always it's going to be infinity. So the statement which is given is wrong, that it is having a finite energy because you are having finitely many coefficients which are non-zero. We could not call it as a finite energy, but we can definitely call it as finite power, because the finite power formula is given by summation mod of AK whole square, where the value of k is from minus infinity to infinity. So because you are having finitely many coefficients, then your power is going to be a finite number. Your power is going to be a finite number which is calculated by this particular formula. Which means that the first statement is wrong. Second statement says that x of t has zero average value because it is periodic. And the statement itself is not correct, right? So there is no dependency between average value and periodicity. There is no dependency between average value and periodicity, which means the second option is also incorrect. Option C, imaginary part of x of t is constant. So if your signal x of t is having two components, one is a real component and the other is an imaginary component, so the third statement claims that, the third option claims that xi of t, the imaginary component is going to be a constant. The imaginary component is going to be a constant. We have to look into it. The last statement is that the real part of x of t is even. The real part of x of t is even. Okay. So now let us have a quick look into the AK which is given. Now you see, AK, does it satisfy the concept of even conjugate? Do you think AK satisfies even conjugate property? Does it do it? What is the problem? Why is it not satisfying even conjugate property? Why is it not satisfying? Because of the presence of the imaginary component at k equal to 0. Because of the presence of the imaginary component at k is equal to 0. Now, if I remove it, then do you think it is going to satisfy? If I remove the imaginary component which is present at k equal to 0, if I remove the imaginary component, is it going to satisfy? Yes. So the problem here is that in order to satisfy the even conjugate property, you should have the real, the k is equal to 0 as a real component or 0. And we had an imaginary component. So what I am going to do is that I am going to separate the DC component from the function. So if I can write my x of t as an AC component and a DC component. If I can write the x of t as an AC component and DC component, so what I am doing is that I am removing the component which is present at k is equal to 0, which is nothing but the DC component. I am just removing the component which is present at k is equal to 0, which is now going to be the DC component, which is 2j. And the remaining part of the x of t, basically x of t, complex Fourier series coefficient is ak. Now let us assume that we have removed the DC component. We have removed it, we have written it separately, the DC component. Now what is remaining is nothing but the AC component. What is remaining is nothing but the AC component. Let me call this function by some other name, which let us call it as ak1. Okay, so AC of t is going to have the complex Fourier series as ak1. So what I have done here is that I have split the function into two parts. One is AC component, the other is a DC component. Now I have removed the DC component, I have written it separately, and what is remaining is nothing but the AC component. What is remaining is nothing but the AC component. So for the AC component, now I am writing the corresponding Fourier series coefficient as ak1. For the AC component, I am writing the corresponding Fourier series coefficient to be ak1. Now please tell me, now it is satisfying even conjugate property. Now if it is satisfying even conjugate property, if this satisfies even conjugate property, can I say my AC component is real? As ak1 satisfies even conjugate property, can I say that AC component of the function, I can say that the AC component of the function is real. The AC component of the function is real, yes or no? I can say that my AC component is real. So when I am writing the real component and imaginary component, the real component is nothing but the AC component. The real component is nothing but the AC component. And you can clearly see the DC component is nothing but the imaginary component. The DC component is nothing but the imaginary component. So basically the imaginary component that you are having is nothing but a constant, which is 2. It is nothing but a constant, which is 2. So I can say that the imaginary part of x of t is constant. Can I say that the imaginary part of the x of t is constant? Because when I separated, it's a DC component. Now this corresponds to the real component. What is left out is nothing but the imaginary component, which is a DC component. So I can say that my imaginary component is nothing but the DC component. Because the real component, we found out that the real component is nothing but the AC component. So the DC component is an imaginary component. As you can see here, the DC component is an imaginary component, which is nothing but a constant. Okay, so I can say, so this corresponds to the DC component. Okay, so this corresponds to the DC component, which value is equal to 2, and it is having an imaginary. Okay, so therefore imaginary part of is constant. The imaginary part of x of t is a constant. Now let us come to the last option, because we know that the third option is correct. The third option is correct. Now let us see the last component. The last option. What is the last option? It claims that the real part of x of t is even. Is it correct? So whatever real component is nothing but the AC component, he says that the real component is even. Is the nature of the real component even? Yes or no? It should be no, because the third option is correct. So obviously the last option has to be wrong. But the question is that why it is wrong and how it is wrong. Please understand. See, if this part, we know this particular part, the real part is, this is the real part. And if the real part is even, then what should be the corresponding Fourier series coefficient? I am only talking about the Fourier series coefficient of the real component or the AC component. Both are same. If this real component or the AC component, if it is even, then what should be the nature of AK? So we have learned that whenever you are having a signal x of t, which is real and even, the corresponding Fourier series coefficient should also satisfy real and even. Did we learn that? The corresponding Fourier series coefficient should give you real and even. Now we know that this real component is nothing but the AC component, and we know the AK of it. So if this is real and even, the nature of AK1 should also be real and even. If this is real and even, then the nature of AK1 should also be real and even. But here it is not real and even. This is of course even conjugate, but this is not real. So therefore the option D is wrong. Are you able to understand? So when I say that the real part of x of t is even, it is wrong, because if the real part of x of t is even, it means that it is real and even. The component is nothing but real and even. So if it is real and even, the complex Fourier series should be real and even. But we know the complex Fourier series of this. We know the complex Fourier series coefficient of it. The complex Fourier series coefficient is not real and even. So if this is not real and even, this will not be even. If this is not real and even, already it is real, but it cannot be even. So therefore the last option is incorrect. So there is a question that how can we say that 2j is DC component? How can we say that 2j is DC component? See here. We have separated this particular 2j, and 2j is present at k equal to 0. K is equal to 0, isn't it a DC component? Any particular component which corresponds to k is equal to 0 is a DC component. And the same DC component we have written it separately. Okay. So we are having a DC component whose value is 2j, and we know that this AC component is nothing but the real component. Because we have seen that AK1 is even conjugate. If this AK1 is even conjugate, then this has to be real also. So if this is real part, this has to be an imaginary part, and which is rightly so. We have seen that it is an imaginary part, and this imaginary part is nothing but a constant. Okay, so 2j is a DC component because it is present at k is equal to 0. Okay, whatever is present at k equal to 0 is nothing but a DC component. Next question. It's a very simple question. So 3 statements are given. We have to see which of the statements are correct. So basically you are having options like this. For the 3 statements above, which of the following is correct? Okay, so please go through the statements which are given in the question. See here, the signal x of t be a continuous time periodic signal. So it is given that x of t is continuous time periodic signal with a fundamental time period t is equal to 1 second. Now ak is the complex Fourier series coefficient of x of t. It is given that ak is the complex Fourier series coefficient of x of t. Now consider the following statement about x of 3t. The complex Fourier series coefficient of x of 3t are ak. Is it true that if x of t is having the Fourier series coefficient as ak, can we also say that x of 3t is also going to have the same Fourier series coefficient? Yes, this is what we have seen from the time scaling property. Yes, it is correct. The second statement, the complex Fourier series coefficient of x of 3t is 3ak, which is not correct because the first statement is correct. So when your first statement is correct, the second statement cannot be correct, right? Because they are contrasting. Third one, the fundamental angular frequency of x of 3t is 6 pi radian per second. The fundamental angular frequency of x of 3t is 6 pi radian per second. Is it correct? We know for the first one, omega naught is nothing but 2 pi by t, which is nothing but 2 pi by 1 second. This is omega naught. Now when we talk about omega naught dash, what is the time period? Here the scaling parameter is 3. So when you are scaling with a scaling parameter of 3, obviously there will be a compression by 3 units. Now the corresponding time period is also going to be compressed by 3 units. So the corresponding time period is going to be 1 by 3. The corresponding time period is now going to be 1 by 3 because it's a scaled function. Okay, so here it is 2 pi by 1 by 3, which is nothing but 6 pi. So the statement which is given in the third one is also correct. So the first and third statements are correct. So if the first and third statements are correct, the answer should be option B. Right? Next question, please. So the Signum function is given. Signum function is equal to x by mod of x. For x not equal to 0, it is equal to 0 for x equal to 0. And we want the Fourier series expansion of signum of cos t. The Fourier series expansion of signum of cos t. So the Signum function here, the Signum function is given as x by mod x for x not equal to 0 and it is equal to 0 for x greater than 0. X equal to 0. Now what is the meaning of this? That signum of x is going to be 1 for x greater than 0 and it is equal to minus 1 for x less than 0 and it is equal to 0 for x equal to 0. Because we know for x greater than 0, mod x is nothing but x, isn't it? For x greater than 0, we know mod x is equal to x for x greater than 0 and it is equal to minus x for x less than 0. There is a mathematical way of writing the mod x function. Now, if I substitute mod x is equal to x for x greater than 0, then this value is going to be 1. So for x greater than 0, I can say that it is 1 and for x less than 0, it is minus 1. So your Signum function is something like this. We know the Signum function is going to be something like this and 1 and minus 1. But the question here is different. The question here is that signum of cos t. But from our understanding of signum of x, signum of x is going to be 1 for x greater than 0 and it is minus 1 for x less than 0. So in the place of x now you are having cos t. So what I can say here is that signum of cos t is equal to 1 for cos t greater than 0 and it is equal to minus 1 for cos t less than 0 and it is equal to 0 for cos t equal to 0. Because in the place of x now we are having cos t. So what does it mean here? So whenever your function cos t is greater than 0, then signum of cos t will be 1. If cos t value, if it is less than 0, then the value of signum of cos t is minus 1 and it is going to be equal to 0 for cos t equal to 0. Now please understand that the cosine function that we are having is something like this. Okay, this is nothing but the cos t function. Now correspondingly, we will plot signum of cos t. Now you see, here we know the cos t is greater than 0. So whenever cos t is greater than 0, then the value of signum of cos t is 1. And here we know the cos t is less than 0. So here the value is correspondingly is going to be minus 1. And the same thing is going to repeat again and again. 1 minus 1 minus. So this is basically the signal that we have already seen. So here there is a minus pi by 2 and here it is pi by 2 and here it is pi. So from minus pi by 2 to pi by 2, the value is 1 and pi by 2 to pi, it's going to be minus 1. This is nothing but an even function. Okay, the nature of this particular function signum of cos t is real and even. Okay, so if signum of cos t is real and even, here we are talking about sine and cosine terms. It means we are talking about the trigonometric Fourier series. We are not talking about the complex Fourier series. Here we are talking about the trigonometric Fourier series. So in the case of the trigonometric Fourier series, what we can understand is that, so whenever the signal x of t is real and even, then correspondingly the Fourier series coefficient will not have the sine components, because you are talking about an even signal. So whenever you are talking about an even signal, it will only have the cosine components. Okay, so sine component is 0 means bk is equal to 0, right? So sine will be 0, it will only have cosine components. So you will be having two options now, option B and option D. So option B says that it is having only cosine components but with all harmonics. Whereas the last option says that it will be having cosine components with odd numbered harmonics. With odd numbered harmonics. Now you see that odd numbered harmonics means we are talking about a property called as half-wave symmetry. Now we already know that this signal we have tested already. This signal satisfies the odd half-wave symmetry. So whenever the signal satisfies odd half-wave symmetry, this will only have the odd harmonics. It will only have the odd harmonics. So the answer for this question is going to be option D, because you will be having odd harmonics, only cosine terms. So therefore the answer is option D. Next question. Right, so you can see the options which are given. This is the signal which is given, and it is also given that AK is going to be the complex Fourier series coefficient. Right, now we have to comment on the nature of the complex Fourier series coefficient. So you can clearly understand that this question is purely based on half-wave symmetry. The signal, this particular question is purely based on half-wave symmetry. Now, when you are shifting the signal by half its time period, as you can see, the fundamental time period of signal, is 3 seconds. From the diagram, it is very clear that the fundamental time period of signal is 3 seconds. So if I shift the signal by half its time period, so here it is 1.5 minus, and here it is plus 1.5. So if I am shifting it towards right, then this part comes to the origin. So this is your x of t minus 1.5. X of t minus 1.5. Because you have shifted it towards right by 1.5 units, the 1.5 is now going to come to the origin. Now let us compare it with the drop minus of x of t. And we know the minus of x of t function is something like this. The minus of x of t function is something like this. This is minus of x of t. Now if you compare x of t minus 1.5, whether it is equal to x of t, of course this is not equal to x of t. X of t minus 1.5 is not equal to x of t. It is not even equal to minus of x of t. It is not even equal to minus of x of t. Right, so what I can say here is that it is not satisfying half-wave symmetry. So quickly you can check the DC component of the function. The DC component itself is also 0. So the problem is not with the hidden half-wave symmetry. Okay, the problem is not with hidden half-wave symmetry. The problem is that this signal doesn't have any half-wave symmetry. So if that is the case, then the first and second options are of course wrong. Okay, the first and second options are of course wrong, because the first option says that there are no odd harmonics. If there are no odd harmonics, it means that it satisfies even half-wave symmetry. And the second option says that there are no even harmonics. So if there is no even harmonics, it is nothing but odd half-wave symmetry. None of the half-wave symmetry is satisfied. So therefore option A, option B are wrong. Now what is interesting about option C and option D is that here the time period is considered as, for C, D, the time period is considered as 6 seconds. And we know that if the signal is having the fundamental time period as 3 seconds, we can also consider the time period to be 6 seconds, 9 seconds, 12 seconds and so on. This is what we have learned, right? So here it is going to be 6 seconds, which is fair enough. Now if you take the half-wave symmetry, x of t minus half time period is 3. And without testing anything, I can say x of t minus 3 will be equal to x of t. I can directly say x of t minus 3 is equal to x of t. Why? Can anyone tell me why? Why can I directly write that x of t minus 3 is equal to x of t? 3 is nothing but the time period of the function. 3 is also the time period of the function, right? So whenever you are shifting the signal by its time period, it will be equal to the same thing. So definitely this will be satisfied. So if this is satisfied, means that I can say the even half-wave symmetry is satisfied. Because you have shifted by half its time period, it is equal to the same signal. Even half-wave symmetry is satisfied. So whenever even half-wave symmetry is satisfied, I can say that AK is equal to 0. The odd harmonics will be 0. So I can say the answer is going to be option D. So this is the only way by which you can have even half-wave symmetry. Okay. Why I told you that even half-wave symmetry can be neglected is because of this particular fact. Okay. Unless and until you consider a time period which is double that of the fundamental time period, you can never have the even half-wave symmetry. Okay. We can never have the even half-wave symmetry. Why? Because when you know that if you consider t as a time period, if you say t as a fundamental time period, in such case x of t minus t by 2, if it is equal to x of t, then t by 2 would be the period. If you are shifting by half its time period, it is equal to x of t, then t by 2 should be the fundamental time period. Yes or no? Because fundamental time period is that particular time period. Okay? So fundamental time period is that particular time period which is minimum, after which the signal is going to repeat. Okay? So if x of t minus t by 2 is equal to x of t, then I could have said t by 2 is going to be the fundamental time period. Right? This is what we have learned, right? X of t plus or minus k t is equal to x of t. T is the fundamental time period, and k is going to be the any integer value. K is equal to 1, 2, 3, 4 and so on. So if I know that t is my fundamental time period, this is satisfied. Fundamental time period itself means that the minimum time period after which the signal is repeating. It's the minimum time after which the signal is repeating. If t by 2, for which it is satisfying, this particular property, if it is satisfied for t by 2, then I would have said that t by 2 is going to be the fundamental time period. I would have said that t by 2 is going to be the fundamental time period. But we know that if I am declaring that t is going to be the fundamental time period, this will never be satisfied. If you are declaring t as the fundamental time period, this should not satisfy at any cost. This should not satisfy at any cost. So therefore, you can never have an even half-wave symmetry unless and until you are considering the time period of the second, the time period of the signal as double the fundamental time period. Okay, this is the only case where you can have even half-wave symmetry. So basically this is nothing but a theoretical case. Okay, it's not a practical case. Practically we can have an odd half-wave symmetry. We will never have an even half-wave symmetry. So the last question of Fourier series. Yes, I will repeat. See here, you are having a signal and we have found out the shifted signal. And how much we have shifted? We have shifted the signal by half its time period. Is this clear? Is this part clear? That how we got the shifted signal? So we have written the shifted signal. We have also written the amplitude reverse signal. We have written the amplitude reverse signal. So you can see that x of t minus 1.5 is not equal to the of plus or minus x of t. So the half-wave symmetry is not satisfied. So the half-wave symmetry is not satisfied. Now what we are doing is that we are considering the time period to be 6 seconds, because in the question itself they have asked in the option C and option D to consider the time period to be 6 seconds. Yes, we can go ahead with that. And now we are checking the half-wave symmetry. What is the half-wave symmetry? X of t minus half its time period, whether it is equal to plus or minus x of t. But we already know that x of t minus 3 should be equal to x of t, because 3 is also the fundamental time period. So therefore, what I can say, the even half-wave symmetry is satisfied formula wise. Formula wise, whenever x of t plus or minus t by 2 is equal to x of t, I can say that it is satisfying even half-wave symmetry. So by that logic, I can say that the even half-wave symmetry is satisfied. So if even half-wave symmetry is satisfied, the signal will only have the even harmonics. The signal will only have the even harmonics. The odd harmonics will be absent in the signal. The odd harmonics will be absent in the signal. So therefore, option D is the correct answer. Option D is the correct answer. So after that, what I told is that the even half-wave symmetry, this is the only possible way in which you can have even half-wave symmetry. Okay, and it's a theoretical concept. Why it's a theoretical concept? Why it is not practical? Because whenever you want your even half-wave symmetry to be satisfied, whenever you want your even half-wave symmetry to be satisfied, it means your fundamental time period is going to be t by 2. It means your fundamental time period is going to be t by 2, because according to the concept of periodicity, x of t plus or minus kt, if it is equal to x of t, k is equal to 1, then you are going to have a fundamental time period. If k is equal to 1, then only you are going to have a fundamental time period. So if it is satisfying for if it is satisfying for t by 2, if it is satisfying for t by 2, it means that now t by 2 will be the fundamental time period. T by 2 will be the fundamental time period. So therefore, I can say that this concept will never happen when you consider that t is going to be your fundamental time period. When you consider t as your fundamental time period, this will never be satisfied, because if this satisfies, then t will not be your fundamental time period. If this satisfies, then t will not be your fundamental time period. So here the question is that we have to find the ratio of power in the 7th harmonic to that of the 5th harmonic. Okay, what we already know is that how to find the power of the signal. How to find the power of the signal? If you expand it, you will be having C0 square, C1 square, C2 square plus so on. The same with the negative side also, C minus 1 square, C minus 2 square, and so on. So the power in the first harmonic, this will be the power in the first harmonic, this will be the power in the second harmonic, and so on. So even if I consider only one part of it, it is also fine. If I consider only this particular part of it, it is also fine. Doesn't matter, right? So one more thing that I know is that whenever I am having a square function, we know that the ck is proportional to the of 1 by k. Whenever we are having a square function, then the ck is proportional to the of 1 by k. Then mod of ck square will be proportional to the of 1 by k square. Mod of ck square will be proportional to the of 1 by k square. Yes or no? Now the question is that c7 square divided by c5 square. C7 square divided by c5 square, which will be equal to 1 by 7 square divided by 1 by 5 square, which is equal to 25 by 49. 25 by 49. So the value which is very close will be 0.5, right? So the last part we are going to discuss about Fourier series is the Dirichlet conditions. Now what are these Dirichlet conditions? That see, when Fourier has given this expansion of Fourier series, that every periodic function can be written in terms of a sine and cosine, or it can be written in terms of a complex periodic exponential. Not many of them have accepted this. This is because of the simple reason that sine function that we are having or cosine function that we are having, these are smooth functions. These are the functions which are continuous and these are also differentiable. But whenever we are talking about any periodic function may not be continuous, may not be differentiable, right? So we have seen the example of a square pulse. The square pulse is an example of a function which is not continuous. If it is not continuous, it cannot be differentiable. And similarly, a triangular function, the triangular function that we have seen is an example of continuous but not differentiable. Whereas a smooth function we are having, which is sine and cosine, are the functions which are continuous and differentiable. So the problem raised by different mathematicians is that how can you represent a particular function which is not continuous and not differentiable, or continuous but not differentiable, in terms of a function which is both continuous and differentiable, for which at that point the Fourier did not have any mathematical background, okay, to establish this particular fact that we can have this particular thing. But yes, it is also possible that the signal is periodic but it may not have a Fourier series expansion. It is also possible that the signal is periodic but it might not have the Fourier series expansion. So therefore, coming to the validity of a particular Fourier series expansion, what are the periodic functions or what are the nature of the periodic functions for which we can have a valid Fourier series expansion, for which we have some conditions. If these conditions are followed, then we can say that the Fourier series expansion is possible for that particular periodic function. Okay, so for the signal to have a valid periodic function, a valid Fourier series expansion, it should satisfy these conditions. Once these conditions are satisfied, then we can say that the periodic function can have a Fourier series expansion. Because these conditions are given by the scientist called as Dirichlet. So therefore we are calling this as the Dirichlet conditions. So basically the Dirichlet has given a set of conditions. When they are followed, then the signal will have the Fourier series expansion. But remember, there might also be a scenario when the conditions are not satisfied, but still the signal can have a Fourier series expansion. So what Dirichlet has told is that these conditions are not the necessary conditions. What is the meaning of necessary condition? Necessary condition simply means that if any of the condition is not satisfied, then the signal will not have Fourier series expansion. This is what is the meaning of necessary condition. Dirichlet told that these conditions are not the necessary conditions. These are just the sufficient conditions. What is the meaning of sufficient conditions? That if these conditions are satisfied, the Fourier series expansion will be possible. If these conditions are satisfied, then Fourier series expansion is possible. If any of the condition is not satisfied, then it may or may not have a Fourier series expansion. Okay, if any of the condition is not satisfied, then it may or may not have a Fourier series expansion. So these conditions, the Dirichlet conditions, are considered as sufficient conditions but not the necessary conditions. So what did he say? What are the conditions that he has established? The first condition that he has told is that the signal must be absolutely integrable in its period. So if you are considering a period, so in that period the function has to be absolutely integrable. So the integration in its period should be less than infinity. This is the first point that he told. The second point that he told is that signal must have finite discontinuities. And the third one is signal can have finite maxima and minima. The signal can have finite maxima and minima. These are the three conditions which are given by Dirichlet. If these conditions are satisfied, then we can say that the signal will have a Fourier series expansion. Okay, so finite discontinuities, we are talking in its period. Finite maxima and minima in its period. So now let me consider a signal, okay, so which is periodic and is having a time period of 1 second, and because it is periodic having a time period of 1 second, its corresponding complex Fourier series coefficient spectrum will be something like this. The corresponding complex Fourier series spectrum can be something like this. Okay, so what I can understand is that as the value of k increases, the value of ck is coming down. The value of ck is coming down, which is something that we already know, that whenever you are having square pulses like this, the ck is going to be proportional to the of 1 by k. So as the value of k increases, you can see that the component is going to come down. Now this is what we have learned. Now what I wanted to do is that I wanted to increase this time period to 10 seconds. I wanted to increase this time period to 10 seconds. So if I increase this time period to 10 seconds, what will be the effect on omega naught? We know that as the time period increases, then definitely the value of omega naught has to come down. As the value of omega naught increases, as the value of time period increases, the value of omega naught has to come down. So the value of omega naught, which is also the spacing between two different frequencies. Omega naught is not only the fundamental frequency, it is also the spacing between the different frequencies. So omega naught comes down, the spacing is also going to come down. The same thing is going to happen if I increase further. So as I increase the value of t, the value of omega naught is further going to come down. The value of omega naught is further going to come down. Now, as I tend the value of time period to infinity, the value of omega naught tends to the of 0. As the value of time period tends to infinity, the value of omega naught is now going to tend to the value of 0. So what I can say here is that as the time period tends to infinity, what is the meaning of time period tending to infinity? So what I mean by the time period tends to infinity is that the signal is becoming non-periodic. The signal is becoming non-periodic. Initially it had a finite time period, and we know after this finite time period it is going to repeat again and again. Now this time period is now tending to infinity. Now if the time period tends to infinity, what I mean to say is that it is not going to repeat. Okay, it is like saying that I've taken money from you, but I'm not saying when I'm going to give back. I just say I'm going to give back. Okay, I say that I'm going to give back, but when I'm going to give back, no answer. Okay, it means that I'm not going to give you. Similar thing is going to happen with the signal. I'm saying it is periodic, but the time period is infinity. If the time period is infinity, then it means that it is not periodic. If the time period is infinity, it means that the signal is not periodic. So what I'm going to do is that whatever formulas we have learned for Fourier series, now to extend the concept of Fourier transform, what I'm doing, which is nothing of non-periodic signal, I'm going to tend the value of t to infinity. So in the same formula, if I tend the value of t to infinity, the tool that I'm going to establish is nothing but the Fourier transform. So basically what we can understand is that Fourier transform is not a different tool to that of Fourier series. It is just a mathematical extension. It is just the mathematical extension as you tend to put the value of t tends to infinity. Okay, one interesting thing that happens in the spectrum here is that the omega naught tends to 0. If the omega naught tends to 0, it means there is no spacing between the two different samples, because omega naught is nothing but the spacing. Now if omega naught tends to 0, it means that the spacing between them is also going to tend to 0. If the spacing tends to 0, it now is going to become continuous. If the spacing tends to 0, now it is going to become continuous. Okay, so initially it was discrete. Initially the spectrum was discrete. Now as the value of omega naught tends to 0, the spectrum is now going to become continuous in nature. So that is why you will see that the continuous time Fourier series spectrum is discrete, whereas the continuous time Fourier transform spectrum is going to be continuous in nature. The continuous time Fourier transform spectrum is going to be continuous in nature. So let us see how we are going to get the formula of Fourier transform from Fourier series. Okay, I am sure this part is understood by all of you. Whatever explained here, the time period is increasing, the value of omega naught comes down, time period tends to infinity, the value of omega naught tends to 0. Okay, so we are discussing about where the time period is tending to infinity. It means that we are extending the concept of periodic functions to non-periodic functions. We are extending the concept of periodic functions to the non-periodic functions. So here Ck, we already know the formula of Ck. Ck is going to be 1 by t integral time period. Here the time period I have considered is minus t by 2 to t by 2 f of t e power minus jk omega naught dt. This is the formula that you already know. So what I am doing here is that in the first step I am going to take the t to the other side. Now it becomes t multiplied by Ck. So I have taken the t to the other side. So t into Ck is going to be equal to integral minus t by 2 to t by 2 f of t e power minus jk omega naught t dt. Right? So now I am assuming or considering that t into Ck is going to be equal to f, which is a function of k omega naught. Which is a function of k omega naught. So t into Ck is going to be f, which is a function of k omega naught. So f as a function of k omega naught is going to be equal to integral minus t by 2 to t by 2 f of t e power minus jk omega naught t dt. Now we are applying the condition, which is nothing but the time period tends to infinity. So if the time period tends to infinity, the value of omega naught is going to tend to 0. If the time period tends to infinity, the value of omega naught tends to 0. Now I am going to replace my k omega naught with the term of omega. I am going to replace my k omega naught with the term of omega. K omega naught with the term of omega. What I mean by this is that we know that the omega naught is going to come down, the spacing is going to come down, now it is going to become continuous. If you remember, when we talked about the continuous time and discrete time functions, so when we had a continuous time function like this, when you try to convert it into discrete time, we replaced t with the term of nts. I'm sure all of you are aware of this. That when we try to convert a continuous to discrete, we replace t with the term of n multiplied by ts. So when you are moving from continuous to discrete, we are replacing t with the term of nts. Now in this case, when you are moving from discrete to continuous, you are doing the opposite. So k into omega naught, we are replacing with the term of omega. Now considering that the spectrum is now going to become continuous in nature. And omega naught is now going to be considered as an infinitesimally small value. Because the value of omega naught is tending to 0, so I can consider omega naught as an infinitesimally small value. Okay, so if I am applying the above constraints, so I can write here f of omega is equal to integral t tends to infinity, t by 2 also tends to infinity, so minus infinity to infinity f of t e power minus j omega t dt. And this formula is what we call as Fourier transform. So one thing which is very clear to us is that Fourier series and Fourier transform are not two different tools. The only thing that we have done here is that we mathematically try to extend the concept of Fourier series to Fourier transform, so that we are getting a formula which is slightly different to the actual formula that you had in the case of Fourier series.